Hello everyone, I am Aswani, Assistant Professor, Department of CSE AIML at MLR Institute of Technology. Let's see today overview of the presentation. State space search, control strategy, characteristics of a problem, exhaustive searches. So in artificial intelligence course, today we are going to deal the state space search, control strategies, characteristics of problem, exhaustive searches. Let's see the overview, the same. State space search, control strategies, characteristics of problem, exhaustive searches. Let's see the first one, state space search. So in last video, we have already seen the general problem solving in which we are having two concepts. The first one is a production system and second one is a state space search. The state space search is also similar to the production system. So it is another method of problem representation that facilitate easy search. It's more convenient to search the problem statement. By using this, find a path from start state to goal state. Here, this state space consists of four components. The first one is a set of S containing the start state, a set G containing goal state, set of nodes, intermediate nodes, and last set of arcs containing a nodes. Each arc corresponds to the operator, means the either operator or action or rule which leads to the starting state to goal state. So let's see the example of the state space search, that is missionaries and cannibals. Let's see the problem statement. Here there are three missionaries and three cannibals at the left side of the river. They need to cross the river from the left side to right side. There is a boat. That capacity of boat is 2. Either they can cross 2 missionaries at a time or 2 cannibals at a time, or either one missionary or one cannibal can cross the river at a time. So here the condition is, if in any of the time the cannibals are outnumbered than the missionaries, the cannibals will eat the missionaries. That is the condition. So here the possible operators that are applied in this problem are 2 missionaries, 0 cannibal, 1 missionary, 1 cannibal, 0 missionary, 2 cannibals, 1 missionary, 0 cannibal, 0 missionary and 1 cannibal. Next, the start state is 3 missionaries, 3 cannibals, 1 boat at the left side, and right side it is opposite, 0 missionary, 0 cannibal and 0 boat. Simply we will represent with 331:000 at right side. Next, the goal state is 0 missionaries, 0 cannibal, 0 boat at the left side, and right side it should be 3 missionaries, 3 cannibals and 1 boat. Simply we'll represent this as 000-331. Okay, we'll indicate left operator, left to right arrow, and right to left this operator. Next, these all are the valid states what we have discussed now, and these are the invalid states. Whenever at the left side or right side 1 missionary and 2 cannibals, then there is a chance the cannibals will eat the missionary. So we can't use this operator. Next, 2 missionaries, 2 cannibals and 1 boat. This is the valid only, but whenever we applied these operators on this, then there is a possibility of eating cannibals eating missionaries. 0 missionary, 1 cannibal, or 0 missionary, 2 cannibals. The next one is, if you apply some operator and you are reaching the previous state again and again, then that is called as a looping state. When we applied that type of operators, that is a waste of time, because iterating the same operator multiple times. So that is a waste of time. So let's see how we will solve this problem statement that missionaries and cannibals. It will start from the 3 missionaries, 3 cannibals, 1 boat at left side, and right side it is 0 missionaries, 0 cannibal and 0 boat. For this problem statement, we can derive multiple solutions. In that, one of the solution is, so it will take initially from left side to right side 0 missionaries, 2 cannibals, and it will goes to the right side. Now left side remaining is 3 missionaries, 1 cannibal and 0. right side is 0 missionary, 2 cannibals, 1 boat. So from this right side to left side, again 1 or 2 persons can come to the left side. So 1 cannibal coming to the right side, left side. So 1 cannibal coming to the right side. Then at left side, 3 missionaries, 2 cannibals, 1 boat. At right side, 0 missionary, 1 cannibal, 0 boat. After that, again 2 cannibals going back to the right side. Then the left side 3 missionaries and right side 3 cannibals and 1 boat. And again it will come from the right side to left side 1 cannibal, because the empty boat can't come from the right side to left side. That is one or 2 persons, 2 missionaries or 1 cannibal or 1 missionary can cross the river from right side to left side. So 1 cannibal is coming back to the left side. Now 3 missionaries, 1 cannibal, 1 missionary at left side. At right side 0 missionary, 2 cannibals and 0 boat. So from here to left side to right side, again 2 missionaries crossing the river. Now at left side 1 missionary, 1 cannibal, 0 boat. At right side 2 missionaries, 1 cannibal and 1 boat. Now here look at this one. This one is the missionary and this one is the cannibal. If you take 1 missionary at left side, what happens here? 2 cannibals are there and 2 missionaries will be there. That's why 1 missionary, 1 cannibal we are crossing. If you take 1 missionary, there is an invalid state. So the cannibal can eat the missionary. That's why we are taking 1 missionary, 1 cannibal from right side to left side. So now the state is at left side 2 missionaries, 2 cannibals and 1 boat. At right side 1 missionary and 1 cannibal. Now 2 missionaries crossing the river to right side. Now left side 0 missionary, 2 cannibals and 0 boat. At right side 3 missionaries, 1 cannibal and 1 boat. Now again we can take the cannibal and we can take from right side to left side. Now it is left side the 3 cannibals and right side 3 missionaries. Now easily we can cross 2 cannibals to the right side. Again 1 cannibal will come to the left side. Then afterwards it will take 2 cannibals and it will cross the river. Let's look at here. 3 missionaries and 1 cannibal. At last, in this state, left side 0 missionary, 0 cannibal, 0 boat. Right side 3 missionaries, 3 cannibals, 1 boat. From here onwards, it will goes to like this. Let's see the solution path. Not only this solution, we can try to solve in multiple solutions also. So in this one of the solution, so I already said 0 missionaries, 2 cannibals, first time crossing the left side to right side. This one indicates the left side to right side and this operator indicates to the right side to left side. At end, initially it will start with the 3 missionaries, 3 cannibals and 1 boat at the left side, and right side it is a 0 missionary, 0 cannibal and 0 boat. And at the end it is a 0 missionary, 0 cannibal, 0 boat. And at right side it is a 3 missionary, 3 cannibal, 1 boat. When we apply all these operators, we will reach it. And it is also in the sequence way we have to apply. And we can solve this same problem with the different operators also. Next concept, control strategies. In previous video also we have seen what is control strategy, the definition. The control strategy describes order of application of the rules to the current state when we applying the some control strategy. To solve any real-time problems, we need to have one control strategy. So here the control strategy should be such that it causes motion towards the solution. When we are taking, for example, if you look at this first operator, when we take 0 missionaries, 2 cannibals, later again we are taking, for example, 2 missionaries next time, then it is a looping statement. When we apply some control strategy or some rule, it should be leads to the solution, not to the looping or not to waste the time. So that is what the first one is. It causes the motion towards a solution. The second one is it needs to explore systematically to the solution space. So DFS and BFS are systematic control strategies which are called as blind searches, uninformed searches, or exhaustive searches. Next, there are two directions in which a search could processed. The first one is a data-driven search or forward chaining search, which will start from the start state and it leads to the goal state. That is a start state search or a data-driven search are called as a forward chaining. The next one is goal-driven search or called backward chaining. It will start from the goal state to and it reaches to the start state. Let's see one by one. Forward chaining. In forward chaining, the process will start from the start state and it will apply the some rules to leads to the goal state. So here forward chaining begins known facts and works towards the conclusion, which means the goal state. Next, for example, if you take 8 puzzle problem, in 8 puzzle problem, for example, this is the 8 puzzle initial state problem, for example, initial state and goal state is 1, 2, 3. For example, then we have to start from the initial state and we need to reach the goal state. For this, we need to apply the operators called left, right, up, down. So these are the operators. All these are called as the tiles and it is arranged in such a way. That is the initial state and we need to lead to the goal state. This one is the goal state and here we need to apply some rules called these. So we are moving this empty tile with the left, right, up and down so that we can reach the goal state. Okay, we'll start from the initial state and we'll reach the goal state by applying some rules. Okay, next here the language OPS 5 uses the forward chaining and here the rules are applied in the form of if then rules. So first we'll apply left, whether it is leading to the conclusion means goal state, then it will explore that left side branch, otherwise it will goes to the right side. Each and every time it will compare with the goal state, how many are misplaced, how many are in the exact position. In such a way it will be leads to the goal state. The next one is backward chaining. So here it will start with the goal state and it will every time it will compare with the start state and how many misplaced tiles are there, then it will reach to the start state. Let's see. Goal directed strategy begins with the goal state, continue working backward from goal state to start state. It will generate the more sub goals, must also be satisfied to the main goal, satisfy main goal until reach the start state. Okay, so here the famous AI programming language Prolog uses this strategy, backward chaining strategy. So if you apply the 8 puzzle problem by using backward chaining strategy, then it is somewhat difficult. We can apply this backward as well as forward to solve this 8 puzzle problem, but which state is nearest or closest to the start state, we can't predict that one. So either applying the backward chaining to this 8 puzzle problem, we can directly go with the forward chaining problem. So if there are large number of explicit goal state and one start state, then it would not be efficient to solve using the backward chaining strategy. That is one of the drawback using the forward chaining strategy. The next concept is characteristics of a problem. There are 5 characteristics of the problem. First one, type of problem, decomposability of problem, role of knowledge, consistence of knowledge base used in solving problem, requirement of solution. The first one is type of problem. There are 3 types of problems. The first one is ignorable, recoverable, irrecoverable. These are the three types of problems. Ignorable. For example, if you are solving some problem, in that, for example, alpha equal to 1, beta equal to 2, and we need to reach some goal, then whether we are applying some control strategy to solve this problem, after some time we realize that it is not used to reach the goal state, then we'll stop that one. We will ignore that kind of solving, then we'll apply another strategy to lead the goal state. For example, if you started and after some time you have realized that it is not useful to solve that problem or reach that solution, then we'll stop that solving that lambda or alpha or beta, anything. Then we'll ignore that one and will leads to the goal state by applying some control strategy. That is ignorable type of problems. The next one is recoverable. Recoverable means, for example, if you try to move some, for example, if you are playing something and you made a one move, and after some time, means the opponent takes that second his turn. In that period only you have realized that you made wrong mistake, you made some wrong move, then you will recover that one, means undo the previous move. Then that is called as recoverable. Whatever we will do, we can recover that one and we can make another move. Next one is irrecoverable. Once if you move that turn, or if you move something in the chess, then you can't undo that move. That is irrecoverable type of problems. Ignorable, recoverable and irrecoverable. In ignorable, will ignore that type of problems. In recoverable, will undo that possibilities. Next, irrecoverable move means once if you make a move means we can't undo that type of problems. The next one is a decomposability of a problem. So in decomposability of a problem, we'll divide the problem into multiple problems, sub-problems, and we'll solve that sub-problems. And we are having a technique called divide and conquer. We'll use the divide and conquer technique. Okay, we'll divide the big problem into sub-problems and we'll solve that problem. Next, role of knowledge. The knowledge about the specified task or problem, facts and rules are called as knowledge. The next one is consistency of knowledge base. Whatever problem knowledge is there, that should be consistent one. The irrelevant information, wrong information leads to the wrong solutions. So here, for example, if it is a humid, then there is a chance of rain. Okay, if it is a humid means rain. If it is a sunny day, then it is a daytime and nighttime. For example, if it is the condition, if it is a humid, then it is a rain. Okay, if it is a sunny, then it is a daytime and a nighttime. When it is a sunny, then definitely it is a daytime, it can't be nighttime. It is a irrelevant information about the problem. So if the knowledge having the inconsistency, then it leads to the wrong solutions. That's why consistency of knowledge base is very important. The last one is the requirement of solution. So there are two types of solutions. One is the absolute solution. Another one is a relevant solution. So for absolute solution means, for example, 2 plus 3 equal to 5. That is the absolute solution. In some cases, to solve the problem, we'll use such kind of things. The approximate value is a relevant solution. So these are the 5 characteristics of the problem. Type of problem, decomposability of a problem, role of knowledge, consistency of knowledge base used in solving problem, requirement of solution. Let's see the next topic. Exhaustive searches are uninformed searches are blind searches. So these searches are used to traverse the graph or tree. Breadth first search, depth first search, depth first iterative deepening, bidirectional search. So in breadth first search, we'll go with the level by level. First we'll start with the start node, later we'll go for the depth 1, then it will complete all the levels of that branches, later we'll goes to the depth equal to 1. In such a way it will traverse the graph or tree. The next one is a depth first search. This search will happen column wise. First it will start with the start node, d equal to 1, depth equal to 1. It will goes to the left side. It will complete the entire branch of the left side. Then only it will goes to the previous node, immediate previous node. Next one is a depth first iterative deepening. In this, it will start with the depth d will be taken. First, it will start with the d equal to 0 and it will complete the till depth, and later it will goes to the BFS also. Later, it will goes to the d equal to 1. For example, 1, 2, 3, 4. These are the nodes. When d equal to 0, only it will traverse in the first node. When d equal to 1, then it will start with the 2, later goes to the 3, later goes to the 4. For example, d equal to 2, next 5, 6. For example, like this, then it will start with the d equal to 0. So it is not goal state. Then it will comes to the 2, later it will goes to the 5. After that again it will comes to the 2 and it will complete the 6. It will visit the 6. Later it will goes to the 3. Later 7, 8. Again it will goes to the 4, 9 and 0. In such a way it will traverse the graph or tree. Depth first iterative deepening. First it will finish the left side. Later it will goes to the immediate parent previous node. Again it will move to the left next node. The next one is bidirectional search, which means there are two types. Search will happen, forward direction and backward direction. So this one will start from the forward direction, and in the same way it will start from the backward direction, and at some common point it will reach that one and it will start finding out the solution from the forward to the back, means goal state. We'll discuss one by one in the next sessions. Let's see the next one, breadth first search. The BFS strategy for traversing a tree or graph. So breadth wise in a tree, already we discussed, level by level will move to the graph. Next, BFS algorithm starts searching from the root node of the tree and expands all successor nodes the current level before moving to the nodes of next level. The breadth first search algorithm is an example of general graph search algorithm. Breadth first search implemented using the first in first outcome queue data structure. Let's see the algorithm. We'll take one example. So, A is the start node and G is the goal node. Okay. So here the input is of course a start node and goal states, and local variables open, closed, statex, successor, found. So why open? Whenever we exploring that nodes, we need to keep the track of in open list. The closed, after visiting, we'll move that node into the closed list. Next is statex. Whenever we are comparing that node into the goal state, we need to call that one to pronounce the node. We are taking statex that name. Next is successor. So whenever we explore the nodes of A, then B and C are the successors of the A. Next, found is a Boolean variable. When it matches the goal node, then it returns a true, otherwise it returns a false. So the output is yes or no. When we reaches the goal state, then it is set yes, otherwise it is no. Let's see the method. Initialize open list with the start node. So there is a open list. In that, first initialize start node, that is A, and closed is 5. Later found equal to false. Initially it is found equal to false. We have take as a false. Then we will compare each and every node with the goal node. Later we will change that found equal to true or false, like that. why we have taken loop means we need to iterate all these nodes A, B, C, like that. We need to visit all the nodes. That's why we have to take a loop. That's why while open not equal to pi, it is not equal to pi, and found equal to false is found equal to false. Then remove the first state from open. This one is open. First state from open and call it as state x by pronouns. Then we have taken state x. Now A is a state x. Put state x in the front of closed list maintained as a stack. First in, first out. So here we moved A into the closed list. Now comparing. If state x equal to goal, what is the goal? G. It will compare A equal to G. No, it is not. Then we can't found equal to true. We can't change the vector value. Now we will move to the else block. Perform expand operation on state x. When we perform expand operation, then B comma C are the successor nodes producing list of successors. What are the list of successors? B and C. Remove from successors those states, if any, that are in the closed state. There are no nodes in the closed state. Append successor at the end of the open list. So B, C. Then again it will goes to the while loop. Open not equal to pi and found equal to false, true. Then it will goes to the loop. Remove the first state. So we have to remove the B. Later call it as a state x and move to the closed list maintained as a stack. Next, state x. What is the state x now? B. B equal to G. No. Then again it will move to the else and perform expand operation. Not visiting, just it is exploring the B successor, B node. Now D and E and move the B into the closed list. Now again it will goes to the while loop. Remove the first state. What is the first state here? C. C equal to G. No. Then again goes to the closed list C. Next, perform the expand operation on C node. So F and G. In such a way, each and every time it will compare the state x to the goal node. If it is yes, when we reach with the G node, then G equal to G. Yes, it is true. Then found equal to true. It will comes to the next block end while. If found equal to true, yes, it is true. Then return yes, stop the algorithm. This is how the breadth first search algorithm works. Next, advantages of BFS. BFS will provide the solution. If in the previous example there is no G state, but we are trying to search for the goal state, then it can't give the optimal solution. If goal is there, then definitely it will give the solution. If solution exists, then definitely it will give. If there is more than one solution for a given problem, then it will give the minimal solution which require the least number of steps. Disadvantages. So here lots of memory, since each level of the tree must be saved into the memory to expand the next level. So lots of memory is required. Next, BFS needs lots of time. If memory is requiring means we need to explore each node, then of course it will take the lots of time. If the solution is far away, for example, in this solution G is the goal node. If you take B as the goal node, then the time is also decreases to search this B as a goal node. So if it is a far away, then it will take the lots of time. Let's see the example for water jug problem. Already we have seen the last video, water jug problem, the production rules. The same production rules will use here also. Okay, initially the start node is 0, 0. Goal node is 4, n. The n can be anything. There are 2 jugs, 5G jug and 3G jug. There are no marker on that 5G and 3G. We need to fill 4G water in the 5G jug, and 3G jug can be anything. Either it can be empty or it can be filled with the water. There is no specification on the 3G jug. So it will start with the 0, 0. in this state, either there are three operations possible here. One is filling the water, another one is emptying the water, and the next one is transfer the water from one jug to another jug. Only these three operations can be possible on this problem. So the first state is 0, 0. Already it is empty, so we can't perform empty. We have to fill the water. We can't perform the transfer. So there are two branches. One is filling the 5G, another one is filling the 3G. We'll start with the BFS will traverse from top to down and left to right. So it will start with the left side 5, 0. And the 5, 0, either we can perform emptying the jug, or we can fill the jug of the 3G jug, or we can transfer the water. So here we performed emptying the 5G jug. Then we leads to the previous state. That's why we have eliminated that one. Later, next one, we filled the water 3G jug also. Then the state is 5, 3. Next, we transfer the water 5G into the 3G 2, 3. That is the production rule 8. All these are the production rules. Okay. Next, on the 0, 3, I means 5G jug and 3G jug. Here also either we can fill the water, or we can empty the water, or we can transfer the water. Again, it will comes here. So it leads to the previous state. That's why we eliminated. Next, 5, 3, we can empty only. Because we can't transfer the water, we can't fill the water. Already it is full of water. That's why we can empty. Next, on 2, here we transfer the water from 5G into 3G. Now the state is 2, 3. On this 2, 3, we can again transfer the water, or we can empty the water jug. Now here on 0, 3, we can perform the same operations. Which one leads to the goal state will move into that state. So on 3, 0, again we can fill the water, we can transfer the water. Here we are empty the water jug, so we are leading to the previous state. That's why we eliminated. In such a way, we'll reach some state. Let's look at this state. We'll reach this one with the goal state. Let's look at it. This one 2, 3. So 5G and 3G. Now we are applying the fourth production rule, emptying the 3G jug. So 2, 0, and 2, 0 transferring the water. The next state is 0, 2. Now again filling the water here. Next 5, 2. Now we will transfer the water from 5G jug into 3G jug. Now the goal state is 4, 3. I already said there is no specification on 3G jug. So 4, 3 is our goal state. In such a way, whatever rules are applicable on the particular current state, we can perform these three operations and we can lead to the goal state, from start state to goal state. So here the path is 0, 0, 5, 0, 2, 3, next 2, 0, 0, 2, 5, 2, next 4, 3. This is the solution path for water jug problem using BFS. So let's see the summary of the today's session. We have already seen state space problem, state space search, and in this we have solved the cannibals and missionaries problem. Next, control strategies. In these control strategies, forward and backward. Forward chaining or backward chaining. Next, characteristics of problem. Type of problem, decomposability of problem, role of knowledge, consistency of knowledge base, and requirement of solution. Those are the characteristics of the problem. Next, we have started exhaustive searches. And we already discussed BFS. The rest of 3 will discuss in the next session. Thank you.